Thank you everybody for coming. My name is Friedman. Yes, I haven't been here in a long time. I hear all the jokes, right? And I think it's funny. Every time I speak, I have a beard. And ironically, my Twitter profile is reshaving, but it's just funny. I've spoken to my it's always off in the summer, so I got what's the
What is the background of that?
Yeah, I know. It's a little stuff. Anyway, so today we're talking about WebAssembly. So a few things I want to get out of the way. Okay. So first of all, this is going to stay away from all the sales pitch stuff. So online you'll see why WebAssembly is amazing and all that kind of stuff. I'm not going to talk about any of that stuff. All right. Honestly, the entire reason I'm giving this talk is just because I found it to be interesting, and it's just something that I think people might find interesting. But there's really very little education. Staying away from all that is just purely it's fun for me to talk about. Hopefully, it'll be fun for you guys to listen to. And last and key point, I'm by no means an expert. Honestly, I just know a little bit more than all you guys know now. By the end of the talk, you'll know exactly as much as I do. So please don't ask any questions because it's going to feel like a facade. So please don't. But honestly, this is just me. I had to throw in a meme because Ellie Goldie would have killed me if I didn't. So yes, I just kept copying Stack Overflow. This is very true when it came to Wise and just kept copying and pasting. These days it's not Stack Overflow. ChatGPT is great for that. So honestly, it just got it working. But that's it. Okay? So let's get into it. All right, so what is WebAssembly? So if you look up the definition of WebAssembly, often you'll find this kind of definition. It's going to say WebAssembly, short to WASM, is a binary instruction. WebAssembly, short to WASM, is a binary instruction format for a stack-based virtual machine. Okay? No good? Good? No good? All right. So again, I'll read it again. WebAssembly, short to WASM, is a binary instruction format for a stack-based virtual machine. What does that mean? Okay, let's dissect that. Whoops. Let's dissect what that means. So where we're done. All right. So we can tab here. I will zoom in. Yes, I will zoom in. Okay. So oh man, I gotta zoom in this also. Can you guys see? Alright. So this is a little C programming. Yes, I will be doing a lot of C programming today. Not that I'm an expert in C at all, so if anybody here doesn't know C, please don't make fun. I want to explain first of all what a virtual machine is. Okay, that's kind of the purpose of this program. To explain just a simple virtual machine. So we don't know the term about virtual machine. You know, we have a Mac and you run Parallels or whatever. That's not the context of this. Not what a virtual machine is. It's more along the lines of like the Java, JVM, Java, or .NET runtime is running a virtual machine. What is that? Effectively, we're virtualizing. Think about it, we're virtualizing a CPU with certain instructions. At the low level, where as the way the CPU works, it's got a bunch of instructions. It can access registers, it can access different things. A bunch of instructions that the CPU understands that we can write to it, and the CPU will do whatever it is. So a virtual machine is effectively we're virtualizing a fake CPU that doesn't actually exist, and there's a whole set of instructions that we can run. So I know that didn't make a lot of sense yet, so let me explain a little bit more, right? So let's first start out with this struct. The struct you see is effectively just a data structure. We have two things. We have an array called a stack, okay, and we have a stack pointer. All right, just keep that in mind. So we have just a stack, it's an array, all right, and we have this thing called a stack pointer. Then we have this other another struct called an instruction. Where is it? All right. So we have this enum instruction set, these different instructions, and we have this struct. Let's actually start with this one. So basically, there's the concept of an instruction. What's an instruction? An instruction basically is either push or pop or add, and each instruction has along with it a value that we're going to either push onto the stack or pop onto the stack. Okay? Still doesn't make a lot of sense. I'll get there, I promise. So let's go through the actual program. We'll do one by one, and then we'll kind of balance back and forth and start to understand it. So here's my little quote-unquote program. I have a program. What this program does, first, it pushes 300 onto the stack, and then pushes 400 onto the stack, and then it calls add. So this is written in my low-level assembly language. It's written, we have these instructions. It's going to push 300, it's going to push 400, and then it's going to call add. What does that do? So we're going to go into execute over here. We're going to execute, we're going to pass in our VM, I'm passing our program, and we have to pass in, this is the C, we got to pass in the size of the array. You can ignore that, but over here, here's what we're having, right? So we got the VM passed in by pointer, and effectively what's happening is as follows. Every one of these instructions, that's what this program is, an array of instructions, like we saw before, the add, the push, the add. We're looping through it, and for each one, we're basically saying, okay, what is the instruction? If it's a push, then we're going to actually loop push. The operation do, we go over here to push, And what it does, you can ignore this if check. It basically just, we have this, remember, our VM has a stack, it's just an array. It takes the number that you passed in here and puts it into the first slot of the array. We put 300, pushes it onto the stack. Okay, so our array is effectively a stack. Now, right now, stack pointer, it started at 0, it's pointing at 0. So we're saying, again, don't let these arrows on the C syntax a little funky, but since this is a pointer, so therefore we don't use dots in C, we use these arrows. But the point is that we take this stack, this array, and into the first slot of the array, we put that number 400, and then we advance the stack pointer now to number 1. Okay? Come back around the loop again, we call push again, and we push the 400. What happens now? Into the second slot of the array, right, into the top of our stack, we push 400. So now we have at the top of our stack, we have 400, underneath that we have 300. Then the next instruction that gets executed is the add instruction. What does the add instruction do? Let's go back to our execute function here. We're running our program. We call add. What does add do? Let's go into the add function. Add pops off the top first two elements of the add of the stack, adds them up together, and pushes it back onto the stack. Okay, so if you're following along in this stack now, after I've run my program, the top of the stack is going to be the value of 300 plus 400, which equals 700. Okay, so then I have a function, just a helper function, just always print whatever's currently on top of the stack. Let's run this. Let's see if this works. Okay, let me just clear my screen here. Okay, and as you see, we got 700. So my little program, very nice, it's working, we pushed onto the stack. Okay, it seems extremely silly at this point, but that in a nutshell is what a virtual machine is. A virtual machine is just a series of instructions that we can, it's a program that can execute a series of instructions. It can manipulate the stack, it can manipulate, again, this is a stack-based virtual machine, so everything's done on the stack. In other CPUs, we have the concept of registers, you can access registers, effectively, et cetera, et cetera. But that's the idea, honestly. That is how the JVM, that's how all these virtual machines work. There's just a whole bunch of instructions that can manipulate different bits of memory. So in our simple, stupid little VM, all we can do at this point is just add and push, and that's that, okay? Let's go one step further. Also, I have this little thing I commented out of here with, change to 0, okay? And then we'll come here, and I'm going to do, what I'm going to do in this case, okay? I have another function that's called write instructions to files. So in this function, what I'm doing is I'm just using basic C, just writing out to a file, all right? So I'm taking out, what I'm writing out is I'm writing out my program. My program is an array of these instructions. Remember, every instruction is a struct with two integers. The enum value, let's just remind ourselves what it looks like. We have, this is an instruction, it's an instruction set, which is an enum, which is effectively an integer. So an integer instruct and an integer, integer instruct and an integer value. So I have an array of these elements over here, that's program, and I'm writing it out to a file. So we're just using basic C, just write it out as a binary thing, just write it out as a binary block to the file system. And then in my next thing, I read it back from the file and I run it. And again, if I run this right now, go back to my thing here, let's run make again. Again, we get the same 700. However, now I created this very cool, let's just do over here, we see we have this program that AVR. It's just a file format I come up with 5 minutes ago. AVR, Vermi, it's my own file format. Effectively, it's just we took this array of, basically an array of two integers, if you want to think about it that way, and wrote it out to fit this. Let's inspect that let's inspect that file for a second. Let's go to hex edit, and we'll do a program.avr. And here's something interesting, right? So there's basically, remember, every one of my instructions is two integers. Okay, two integers. The integer was the enum, add or push or whatever it was, right? What the other? I forgot myself. Push pop add, right? So if add push pop. So the first instruction was to push number 300 onto the stack. So let's look at our hex editor and see if we can make sense of this. So here we have 4 bytes. That's the first. That's the instruction, which in this case is add, which is 0 because my enum. To go back to my code over here, my enum, this value over here, this add. This push rather, it starts out with a push, Starts out with a push is 0, which is why in the hex editor we see first the 0. The next 4 bytes looks kind of interesting, 2C, O1, whatever. Okay, now my machine is a little endian, so it's really 1, 2, so the lower bits come first. But anyway, it's 0, 1, 2, C. Let's just kind of open up another program here. We'll do Python 3. Zoom in for a second. Whoops. Okay, and these bytes over here, let's just come here, was 2. So let's do, it's basically 0, 1, 2, C. That's really because we're going to flip. 0, 1, 2, C. Let's see what that is. Still enough to get used to I3, guys. So we'll do x, the 0x, what was it? I remember myself. 0, 1, 2, 0, 1, 2, C, and there it is, there's my 300, right? So I just took my code, right? It got converted to binary. It's now written out as this binary file called, which I very stupidly named, .avr. But here it is, okay? So, let's call this, there we go, okay? The point I'm trying to show here is that I just wrote this whole virtual machine, okay, this whole cute little program, which is a virtual machine. Again, I only have 3 instructions, push, pop, add. We can have a bunch more instructions. And I've written out my program. This is my program, right? This is my little program over here. I wrote out to a binary file. So now we have this binary file that represents my program. Okay, so I'm just laying that ground rules for some basic concepts. Make sense so far? Hopefully? Okay. Now let's go into another little, one more demo. So let me just kill this real quick. Let's go back here. Let's go up a level. That up. Okay. So a very similar demo, except now my virtual machine has one additional thing. It has also memory. Okay, so previously my virtual machine just had the stack, right, and then had a pointer or whatever. Now I'm adding another thing, which is an array that's going to be sort of quote unquote our RAM, our memory. Okay, and to deal with that, we have a few more instructions. We have these 3 that we had before. I also added multiply, but I also added store and load. What store and load does, it allows us to store data into memory, allows us to load data from memory. Again, this is what a virtual machine typically can do. It can access memory. So that's what I'm trying to demonstrate over here, is that my virtual machine has the stack that it did before, but also now it has memory that we can actually put stuff into. Okay, how do we use that? If you go back over here into my execute program, you'll see this is the same loop as before. The first 3 are the same, except now in multiply is just add multiply, which is multiplication. But over here, what we're doing is, in the case of store, what we're basically saying is, okay, the way someone is going to, let's actually look at the program over here first. This will make a little bit more sense. So I wrote a program that does the following. It does 10 plus 20 multiplied by 3 plus 1, right? So we got the order operations. We got to first do the parentheses first. So first we got to do 10 plus 20. We got to stash that somewhere. Then we go to 3 plus 4, stash that somewhere, take the result and multiply the 2. And that's what my program over here is doing. It's basically pushing 10 onto the stack, pushing 20 onto the stack, and then adding it. And then what store 0 does basically says take the value at the top of the stack and store it into slot 0 of memory, not the stack. Right now we have this random access memory, quote unquote, we have this piece of memory we can stick arbitrary values into, and that's what we're doing. We're storing the value at the top of the stack, in this case 30, we're putting onto the stack. Then I say push 3, push 4, do add again. Now I'm saying load 0. So now what's going to happen is, because after the add statement, my gosh, this is annoying, after the add statement, the value at the top of the stack is going to be 3 plus 4, it's going to be 7. Right? And then we do load 0, we say go to slot 0 in memory, not in the stack, and load that onto the stack. So now we're going to have the second value of the stack is going to be our 3 plus 4 is 7, but the value that we just loaded from memory is going to be 10 plus 20, which would be 30. And now we do multiply, we do 30 times 7. Makes sense?
Why do you need to do that though? Because it would still be on the stack even if you don't store it.
I could have done it without that.
You could have done it.
I probably could have done it without that, yes. Just demonstration.
Yeah,
this
just-
helps. Yeah. Okay? Okay, this one's paying attention. Good. Okay? Fine. So hopefully that makes sense, because let's go back here. That is effectively what WebAssembly is. WebAssembly is, let's go back to our first slide actually. Right? WebAssembly is a binary instruction format for a stack-based virtual machine. So if you remember in my little sample, the AVR file, my binary file, that is analogous to WebAssembly. That is what WebAssembly is. It's a binary format, just like my AVR file, that represents an instructions for a stack-based virtual machine. So obviously, a stack-based virtual machine for WebAssembly is much, much more complicated than mine, but that is, from a high level, what WebAssembly is. It's a binary format for a stack-based virtual machine, okay? So just like in our demo, the WASM is equivalent to our binary file. That's the first reason why WebAssembly isn't a great. So my title for my talk was a little hyperbolic, except it's terribly named. But it's just a cute little joke because realistically speaking, it's not actually assembly. Assembly, it's funny. Assembly was meant to be a human readable, right? Before assembly, people were actually flipping bits for ones and zeros. That's how they programmed. They came with the concept of assembly. It's supposed to be human readable. And in the context of WebAssembly actually represents the binary file, which is not human readable. It's just a funny little thing. So it's not actually. So it's kind of misnamed. It's not really WebAssembly. It's not. But anyway. So that's what WebAssembly represents, is that binary file. Okay, but here's a very a key point that I think everybody needs to understand. So I'll read it out. Key point to remember is that just like in our demo, there were no instructions that were able to access anything on the system, right? So in our little sandbox, we were able to add, we were able to manipulate the stack, and we were able to manipulate memory. That's it. There was no way to access the file system. There's no way to make any syscalls. There's no way to do anything outside of our little sandbox of just basically manipulating the stack, manipulating memory. That's it. Okay. WebAssembly works exactly the same way. WASM does not have any instructions. If you look through the entire instruction set of WebAssembly, there's nothing beyond this point of just manipulating the stack, manipulating memory. It can't write to the file system, can't write standard out, can't do any of that stuff. None of that. Okay, it's completely sandboxed in its own environment. Which obviously leads to a lot of problems, like how do we do anything? We'll get to that. But that WebAssembly, important to understand, it can only access the stack and only access the memory, and that's that. Okay? So let's move on. Any questions so far?
The file that your binary file that you had, so you were showing the first value of 300, and you're basically having your 300, your 400, and your 700.
My binary format didn't have 700. My binary format, if you look at the code again, where is it? Actually, not this one, but I'll just speed up. The binary format was just, I took my array of instructions, which was push 300, push 400, add. Took that array and wrote that out to disk. So what you saw in the hex editor was the first 4 bytes, right? The first integer was that 0, which represented push. The next 4 was represented the 300. Then we had the push again, 0. Then we had the 400. Then we had add, which was 3 or something like that, right? So it's just the instructions. Our program, our virtual machine, then reads that binary file from this and executes it, and that's how we get to the 700. The final result is not written to this, it's just the instructions, our program. It's what our compiler it to.
So the file isn't actually a program, it's just something that something else can read.
That's effectively what the program is. If you think about it, what is a program? It's just an
I
executable.
understand, but it's not the language in itself. Someone has to read that and read it as a list of instructions.
Correct. And that's exactly what WebAssembly is. It's just the binary instruction that the WebAssembly runtime, or however it's called, the virtual machine, reads those instructions, the binary instruction, parses through it, and then executes. Okay. So, like I was saying before, WASM represents a binary format, and say that a few times, but there is something called WAT. Yes, that's what it's called. It's short for WebAssembly text format. So yes, while WASM is in fact binary, there is also a text format for WASM. Okay, so it's not just binary. I mean, WASM is binary, but there is something called WAT. There is a documented spec of what the actual. There is a textual representation of WebAssembly. Okay, keep that in mind. Another thing, there's also something called WABIT. WABIT is basically short for something called the WebAssembly Binary Toolkit. This is an open source project that has a lot of awesome tools for working with WebAssembly. Okay. So let's demonstrate this. Let's go back to our terminal. Just kill this for a second. Okay, let's go to. Okay, so here's some WAP for you, right? So I'm not going to kind of go through the exact syntax. It's just a high level. It uses a thing called S expressions, which is type of whatever. But the point is, we have this function called add. Okay, it takes in value of I32, an integer, and it results in an integer. Simple function. And then over here, basically, the local get. This is a way of saying get from the stack, pop up the top of the stack, get the value A, get it, and then add. Looks very similar to our little thing over here, right? So effectively, we're saying get from the stack, get the top value, put it into A, get the value, pop into B, whatever, and then just do add. But okay, this when nobody ever writes code in this particular format, but this is an actual representation. You can write WebAssembly like this if you want to, if you're crazy enough, and you can compile it down to WASM. This does exist. But there's another important thing I want to show you over there. There's something called this export add over at the bottom. Okay, we're exporting something, which is another interesting point that we need to understand. So let me go and run this. Okay, it's just a WAP file. So we come back to our command line, and if I believe I have a make file for this as well. Okay, let's actually look at the make file here. Let me just get a look at the make file. What the make file here does, okay, the make file effectively, what it does, it runs this. It runs WAT to WASM. WAT to WASM is a tool by the WABIT guys. Yes, okay. So inside of WABIT, this thing called WAT to WASM. Effectively, it's a tool that it's in the name. It takes a WAT file and compiles it down to WebAssembly to WASM. Okay, and then I'm just running a Python server, or whatever. Okay, blah blah blah, so that we can actually demonstrate it. Right? Say again.
So this is why you did the talk.
Basically. All right, so I can show you, if I go back to my file system here for just before I kill it, now that I built it, if I go over here, we see that we have over here this add.wasm. Let me just remove it, add.wasm, okay? Let's clean it again, I just do make build. I don't make me.wat, okay, just make. Okay, let's kill that. And if we look over here, now we have this add.wasm. So this add.wasm was created by WAT2wasm. It was when I run my make file, that's what it did. All right, and if we actually go to file, add.wasm, there we go, it's a WebAssembly file, that's what Linux tells us, it's a WebAssembly blah, 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 okay? So now how do we actually use this? So now I took a WAT file, okay? I turned it into a WASM file. We now have this WASM file, how do we actually use it in the browser? So let's go back to our code. And inside here, we have this index.html file, okay? And again, I'm gonna spin up a Python server in just a second, but let's look at, this is all built into the browser, these APIs are built into the browser to actually start kicking off and running WebAssembly. How do we do that? So first what I do is I just get the file, okay? And then this is whatever, blah, blah, blah. This is how we get access to the WebAssembly instance, all right? So we ran this little bit of code, you fetch it, then you get the array buffer, et cetera, and then you instantiate it. Long story short, we get access to something called an instance. This instance represents our WebAssembly thing that we download from the server, the browser starts executing it, and now we have this instance. Now this instance, you'll notice, has something called exports. You go back to my WAP file over here, you'll see that I exported something. So this I didn't show in my own little virtual machine. This is a concept that WASM does have, is this concept of we have a bunch of functions that we can write in our WebAssembly, and then we can then export it. So the tool, the that's running our WebAssembly, can then call into that WebAssembly. So we have a bunch of functions in our WebAssembly. Inside of WebAssembly, we can export it, and then we can call it from wherever we're running it. So in the JavaScript land, what we can do is, come over here, in JavaScript, when we do instant.exports, it has add. This add function was exported right over here, okay? So now, inside my JavaScript, once I have this instance that exports, and I can get access to all, it's an object that has access to all the exports that I got. Okay, let's run this in the browser. Let's go back here, let's run this again. Okay, so let's zoom in on that. Let's okay, promise you it says 5. Okay, there you go. It says 5, promise you, okay? So let me just show you the code just a second again. Let's look at the code. What the code effectively did is it got the WebAssembly, it got the add export, and then it calls the actual function, okay? And if we look over here, let's just for funsies, let's just do const instance, or let's do let instance, okay? Whoa. Get it ready. Instance equals. Is there an end key there?
You could just destructure it.
You can
No, you
destructure
can't
the house.
destructure. Really?
Yeah.
That's valid syntax?
Yeah.
That's not there in JavaScript.
Okay.
Okay, let's refresh over here. I just want to show you now instance over here. Instance, okay? We have instance.exports. There it is. And when you do the add, okay, it's actually kind of cool. Native code, yay, right? You see yourself in native code. Now you actually create your own native code. Feels really powerful. Ooh, native code, right? It looks really nice, okay? But there's the add function that we got from WebAssembly. We got our own little native code. It's very, very interesting, okay? Very nice. All right, that's pretty cool and all. So let's go back to our slides. So, we're talking about exports. Exports is, again, a WASM module can export functions that the WASM host can then call. In our example, we saw how within our JavaScript, we're able to get access to the add method, et cetera, what I just demonstrated. This is the export, so the WebAssembly can export the add function that our JavaScript can then call. But there's also a concept of the imports. This is the opposite, right? Imports are functions that can be defined by the host, and an import into WebAssembly, said differently, is a way for WASM to call back into JavaScript. Right? So what this means is that when we're executing our WebAssembly, we can pass functions from the host, in this case JavaScript, we can pass it into WebAssembly, that WebAssembly can then call. So remember all the way at the beginning I said that, hey, WebAssembly is pretty limited. It can only access its own stack. It can only access memory. It can't access anything else. Slight caveat there. It can't by itself, but it can take in a function passed by the host that can do whatever it wants to. Okay? So let's see that in action. Whoops. Okay? So just a little caveat. For the upcoming demos, we'll be using C. However, we're using a very raw approach, and I'd like to stress this is not how WASM applications are typically built. There's a toolchain known as mscripting that provides a lot more functionality, but in the interest of understanding, basically, I'll just say what I'm over here about. My point is that I'm going to be demonstrating a bunch of stuff now in C with WebAssembly. This is not how you use WebAssembly. Again, I said in the beginning of the talk, this is not going to be practical, and I meant it. This is not how you write WebAssembly. I'm really I'm stripping away all the magic, stripping away all the abstractions, just doing it very raw, taking C and compiling it to WebAssembly, so there's nothing else. This is not how you do it, because it's way more manual. If you're writing real applications, if you're choosing C or many other language, there's a tool chain known as mscripting that provides a lot of the stuff out of it you don't have to worry about. And at the end, I'll show some .NET samples or whatever, just to kind of see how far we can abstract ourselves away from it. But here we're trying to understand the lower level mechanism. Okay? So, let's do it. So let's come back over here. Let's go to 04. All right, so let's bring that up in VS Code. Okay. So let's look at our main.c file. All right. So now we're in C land. But before I show you the actual C, let's look at the make file. So in make, now I'm not sure how many people here know much about C, but I'm using a famous, popular compiler for C called Clang. I don't know if GCC has a way to compile devices. Possibly it does. I'm not sure, but I was using Clang. Clang is a compiler. You can get it on all operating systems. But you have over there on the first line where we're compiling, we're saying we're targeting WASM32. So we're compiling, our C code is going to be compiled down to WASM. Okay, so you can do that with the compiler with GCC, with Clang. You can compile a C program down to WebAssembly. All right. Another interesting thing, we're going to be using no standard library. What that means is when you're writing a C program, you have to import the top line, usually stdlib, that gives you access to writing to file system, all the syscalls, printf, all that kind of typical stuff. In order to actually do anything useful, you use stdlib. We're not going to have access to that because we're compiling the WebAssembly. So there's no printf. You can't write to standard out, right? In Linux, when you're writing out to standard out, you just write the file descriptor one, you write into a file. You can't do that. You can't access anything outside of your little sandbox. So you don't have access to standard library. It's going to be important in a second, okay? Then we have some other flags, blah, blah, blah. And also allow undefined. Allow undefined is a flag that tells the C compiler saying, hey, there's going to be some functions over here that are not going to be defined, and I'm going to call functions that don't actually exist. Just let it happen. Don't worry about it. We got this. And you'll see soon why that matters, right? Okay. So going back to our program here. So now we have this thing, this attribute that we can, this little macro over here. export, basically anything marked as export is going to be a function that is going to be exported to our WebAssembly. All right, so just like we had in our little WAP file, we exported. Now I'm doing it in the C version. I have these two functions, okay, three functions rather. One add, one this and that. I'll explain those in a second. These are functions that are going to be accessible from WebAssembly. All right. Now I just want to show you what happens when I compile this thing. Let's clear this. This would be okay. And if you look over here now, we have this main.wasm file. Okay, this got generated by the C compiler. This main.wasm file. This got generated by the wasm file. And if you're actually curious what it is, we can do wasm to what main.wasm. And there is my blah, blah, blah. If you look through it, you'll see actually not the imports, let's look at the exports. Export add, export func this, export func that, right? So this was generated from the GCC, from Clang. This was my compiler my C program down to this WASM file. And here you can see the WAP format. Hopefully that all makes sense, all right? But let's go back to our C program. Let's see what it actually does. So this function, pretty self-explanatory. But then I have over here these two little interesting things, okay? I have JSFunc with int, JSFunc with string. All right. So these are functions. Now, anybody that's done VC programming knows that you always put your declarations on top, or you put them in a header file. But then you actually, when you call the function, it needs to have some kind of actual implementation. Here they don't. If you look through my entire file, there's no implementation for JSFunc with int or JSFunc with string. They don't exist. What I do have is a function that's called func that will call JS with int. Here's how this is going to work. And you'll see this in a second. Okay. These functions are going to be the imports. So it's a little confusing, so we have to keep track. There's bidirectional here. There's functions that WebAssembly can export to JavaScript, and I'll use JavaScript even though it's not just JavaScript, but there's functions that the WebAssembly can export to JavaScript, and then there's functions that JavaScript can pass into our WebAssembly. Okay, so the first one, when we export from Web, that's export. When we send it from JavaScript back into our program, those are imports. Those two files on top, those two functions on top rather, those are functions that are going to be sent in from JavaScript into our program. So even though our program has no knowledge of them, it's like, okay, allow them to find, the compiler says, well, allow it, and it's all going to be stitched together as you'll see in a second. Those functions are going to be functions that I'm calling from C back into JavaScript. So in my JavaScript, as I'll show you in a second, I'm going to call this function, we'll start with this one, func that calls int. Okay, this is exported, so I'll have access to it in my JavaScript. Then this is going to then go back and call right back into JavaScript. Make sense? Hopefully. Any questions on this?
Yeah.
Yeah, go ahead.
I'm saying compiling, C, it's like an interface sort of, like compiling C and you have JavaScript, right? So how does that work?
So I didn't show the JavaScript yet. We'll see the JavaScript in a second. I didn't show you JavaScript.
So I'm saying, but you're importing JavaScript into C and then you're compiling C. So
there's no JavaScript here. There's no JavaScript here. You'll see this is just a way for me to tell the compiler saying this function is going to be there when we run. You'll see how. It's going to be there. Just ignore it. Don't bother with it. You'll see when you see the JavaScript, it'll make more sense. Anybody else? Okay. So let's look at the JavaScript. Okay. So JavaScript in this case is a little bit more complex. So let's actually index.js file. Where do we start? So I have this function over here called load.wasm, which is just another little file over here. So here's really the main bit. So this is a similar kind of API from before, where instead of this one I'm doing instantiated streaming, different API. But we pass in over here, we pass in a second argument. We pass in first the fetch, then we pass in a second argument. This argument is an object right now, which I'm calling env, okay, which is just basically any object that we get passed in here gets passed through to our instantiation. So when we do up our WebAssembly module, we're going to pass in this object. So let's see how we use it. When I use it, you'll see I'm calling load.wasm, and check this out. Right? This is, to answer your question, these are the functions that are going to be sent in from JavaScript to our WebAssembly, right? So over here I have JSFunc within. Does that look familiar? If we go back to our C program, see that, JSFunc within. So this is me when I'm loading up the WebAssembly, I'm saying here is the function, you're expecting a function called JSFunc within, and it's going to call my function called wasm and callback, which is right over here, which is a simple console log. Okay? And same thing for my JSFunc with string, over here it's got this little thing, whatever it is. Okay? So when I'm loading up my WebAssembly from my JavaScript, what I'm saying is, here are functions that are written in JavaScript that are going to be passed along. So effectively, what ends up happening is that yes, my C doesn't know anything about JavaScript, but when the whole thing gets stitched together, when Chrome, in this case, runs my WebAssembly, it's going to go through and run the instruction. When it comes to the instruction of calling the exported function, WebAssembly is going to, however the browser is going to do it, is going to magically call it back into our JavaScript because that was a function that was imported into our WebAssembly. Okay? So let's see this in action. So also, let me just show you a few more things. I import over here. From my exports, remember, I exported the add function, the func that we'll call JS with int, func will call blah, blah, blah. So let's go over here, okay? So I have a button that says call with int. So hopefully you're keeping track of what's going to happen. When I click on this button, I'm calling it to C. I'm calling the func that we'll call JS with int. This is the function I got from my exports. Inside of that function, what we did, we called back into our JavaScript or imports. So we're going very, very roundabout. We're calling from our browser. We're going to call it into our WebAssembly, which is going to call back into our JavaScript. Let's see this in action. So here we go. Let's pull up the DevTools. So here's my add function from before, whatever. But when I call WASM got the following from WASM 42. Where did that come from? Let's go back to our code. And I see over here I said JS func with that passed in 42. That called back into our JavaScript, and instead of our JavaScript, all I did was got the following number from WASM and got my 42. And that's what I see in my output. Okay, so this is how, even though the browser, even though WebAssembly is limited, we can inject in JavaScript functions to do anything that WASM can. Make sense? Okay. Now let's do the stream one.
What
Okay?
do you gain? Are you able to like then access stuff that are in the context that function was defined in?
It's not a sales pitch.
No, I'm saying, but what do you? What do
It's
you?
okay, I was trying to be funny. The point is that WebAssembly is limited, right? WebAssembly is it's fast and I want to get that. But it is limited. It's purposely on purpose for security.
Does the
It's
function
sandbox.
still have
So
access to the context it was defined in?
Which one?
the JavaScript one. Or
JavaScript one.
Sure. It's a function. It's not what we want. Yeah. Okay. All right. So let's look at my string version. Okay. Let's go back over here, and we'll see that in my main.c, I have a function that goes whatever. Let's look at the declaration. It basically takes in the char star. For those that know C, there's no strings in C. It's just an array of characters, whatever, no terminated function. But question? Okay. So we're passing in this string into JavaScript. Right, so it seems very similar. I have this function, it's going to JS function string, takes from the string. Okay. Now I guess it is important. Maybe I should mention this. In C, there's no real strings. There's character arrays. And the way we know when it stops is because it's null terminated. So anytime you have a string in C, let's say hello world is going to be a little /0 at the end. That's how C knows that that's the end of it. It's just crazy. Whatever. That's just how it is in C when you're dealing with double level. Okay. It's going to be important in a second. All right. So effectively, JS func string. I'm calling my function that I got from JavaScript. So again, let's go through the whole rigmarole. This is going to be called from JavaScript. It's going to be called into here. This is going to call back into my JavaScript, passing in that string. Same as before. Let's go into my index.js. I have this thing over here, WASM string callback, which is what I passed in over here. So when you click on this button, func that will call JS with string, it's going to call into this function, which is going to call back into JavaScript all the way up here, taking me to my string, and I'm just going to follow from WASM, got str. So we should see our little thing, if we did this right, we should see our little hello from WASM message. Okay, let's go back over here. Let's refresh this page and let's click this. And if you look over here, lo and behold, we got the following string from WASM 1024. Why?
That's
Okay.
24 screen.
What?
That's 24 screen.
1024. Okay. So the answer, that was in the details, is because when you actually get values back from C and WebAssembly, you can pass strings. Again, what we could do is it passes just a pointer. Okay, so we're getting the C land, but it basically passes in a pointer. Pointer is just an address in memory of where something lives. So that 1024 represents the address where. So there's, if you look at my code over, hang on. In my second demo that I showed, when I showed the whole virtual machine, I also explained that there's a little bit of memory that your virtual machine can access. In the context of WASM, that block of memory is shared by both the WebAssembly and the browser. In the browser, the host can access that memory. Therefore, that 1024 represents, so WASM took that string, okay, it took the string that I had over here, took the string, put it into memory at address 1024, and it passed in, when it called into the JavaScript, it passed the pointer where in memory we're going to find that string. Now JavaScript also has access to that memory, so it's up to JavaScript to go ahead and dig the value out of memory. So let's do that. It's a little complicated. Whoops. Let's go in here, and I'm just going to uncomment because we're not going to do this live. Better than that.
Shift. Control shift. Whatever command. Add shift. However you do comments. Back.
Actually, use Mac.
Jump right.
I'm not really happy with JavaScript. All right. So. Okay. So now I have this other thing called getString from pointer. What's getString from pointer, you ask? If you don't ask, you're not curious, but maybe you are. There's this function, this little thing over here called cStringLint. We have getString from pointer. So it's a little complicated, so I'll try to walk you through it. Okay. So we have this instance.export.memory. So remember before I was talking about instance.exports, that's how we get access to functions. Instance.exports.memory represents this block of memory that's shared between both WebAssembly and our JavaScript. That's what that memory is. Okay. Then I have this function called cString that takes in that memory, and it takes in the pointer. Effectively, what it does is it does first have a cStringLint function. Again, strlen for the C program is a way to find the length of a string. Yes, you need a function that, because all it does effectively, it starts just walking through, address by address until it finds a \0. So what we're doing over here is here's the memory, which is the buffer. This is the memory that I got from WASM, and here's a starting point. And we're basically just counting, just keep counting this len thing over here. As long as we don't equal to a \0, as long as we don't find the 0, keep counting. That gives the length of the string. So we have to be very, very manual. Okay, just like we see, we got to just right, fine.
Why do you need two instructions then? Why can't you just return the string once you hit the null time?
because the way I'm using this text decoder, which takes an array of bytes. So the way the browser has this thing called, you basically create this uint array from that buffer from the starting point and the length. So could there be other ways? It's very possible. This is not a judgment. Okay, so the point is that we can then take, so now that I have the length of the string, I can new up this uint array, which uint8 array basically takes the buffer, where we're starting and how long. So effectively we're saying is from this whole chunk of memory that we have access to, what we have access to, give me a slice of that starting at pointer and length, and then pass it into the decode function, which is going to turn back into a string. Okay? And that's going to come back over here. So now we've got that function over here. Let's run it back. Let's go to the browser. Let's refresh. There we go. And nothing happens. So on, and now we actually got to find out. Make sense? Okay, cool. So that's all very nice and handy. Let's do something for real. Let's actually do some kind of something useful. Instead of just writing stuff, let's actually build a real application. I'm going to say, let's build that. Let me show you what I built. All right, so let me first show you the final product, and then we'll walk through it. Okay, so let's see something on the screen. So, very snazzy. All right, so we got this little animation. Looks pretty insane, but it's pretty cool. We click on it, the ball bouncing around. Very nice. All right. So this was actually written in C. Okay, the heavy lifting, the logic of this was written in C. I just interfaced with JavaScript when I needed to. All right. So let me kind of walk you through the code. Where do we start? Start with the index.js, I guess. Okay. So, I don't know where to start with this stuff. So we have this clear canvas function. Okay, let's start with init. Let's go to start with any. Let's go to start with init. Okay. So what is init? This is really where the JavaScript kicks off, where it starts everything, right? We call it init function. What is init? Init is a function. If you scroll up over here on top, you'll see init is actually a function written in WebAssembly. It's imported from my C code. What's that? Let's go back over here. Now, if you remember, I mentioned this is a very, very raw, low-level doing. You don't have stdlib. You don't have any standard library, right? Which means even random is a library of something that I have to write myself. I wrote this myself. You basically have, we need an actual library. We need random, because right? And another thing that if we know how random works, right? Random, we need to seed it with something. What do we typically seed random with? The current time. You don't have access to the current time of WebAssembly, right? Which is why, so we have this function over here, init rand, okay, which takes in some number, but if you look at how I'm calling it, so this is what I'm doing here in my JavaScript, I'm saying init date.now. Let's get the current tick or whatever from the system clock, pass it into WebAssembly, and that's how we can kick everything off, and that's how our WebAssembly function, why am I going to the wrong file? Right? Inside here, we call init, we can init our rand with C that's passed in. Then we also have the width and the height, and we have these two variables up on top. We're basically setting the width and the height, so we know the width and the height of the canvas inside of our C program as well. Okay? So the JavaScript is the one that creates the canvas. The JavaScript knows the size of the width and height. We need to pass it into C. C is going to need to know that for collision detection, as you'll see in a second. All right? Fine. Go back to JavaScript, and we call request animation frame. Game, fine. Clear canvas, nothing interesting. It just basically redraws using some JavaScript APIs. It just, where is it? It just basically fills it, like clears the entire canvas. Again, nothing exciting. Then what we do is we do set ball count, skip all that. We call draw. This is where it starts getting interesting. Okay? What draw does, it calls into C. Okay, let's look at that. Draw is a function from C. So maybe we should start paying attention to what the C code is doing. So in C, I have a struct called ball. Ball represents a ball. So I don't know if anyone ever had the joy of making balls bounce around the screen. It's actually a fun little thing, nothing too exciting. But the point is, I'll explain the algorithm real briefly. We have the x and the y, which is the top left coordinate of the ball, or it could be the center, depending on when you program it. In my version, x, y is the top left coordinate of the ball. Radius is how big it is. And then we have the dx and dy is the delta x, delta y. How many pixels is it going to move every single frame? That's what this is. So that's what dx and dy represents, meaning every single. So the way animation works, right? We clear the screen, we paint something in a specific spot, we do update, we move things around, clear the screen, paint it again, and if you do it fast enough, it looks like something is effectively moved. That's what we're doing over here. We have these balls, x and y, and then every single time we're going to update x and y based on the current position, based on the velocity of the dx and dy, and it's just going to redraw. So if you look at the update, rather the draw ball function, draw, you'll notice over here what I'm doing is I'm looping through each one of these, and I'm calling platform draw ball. Okay, so this is in my draw function. This is a function that was exported. So remember my JavaScript, I'm calling this as draw. This was being called every single tick around the animation, the request animation frame, I'm calling this draw function, right? And what it's doing is it's looping through all the balls, and it's basically calling platform draw ball. It's calling what is platform draw ball? You'll see over here platform draw ball is a function. Again, no implementation. This tells us this was by JavaScript. So in order to draw the actual ball, I can't do that from C. I need to actually do that through WebAssembly, through JavaScript. So over here inside of draw ball, you'll see I have a lot of code. But let's look at this part right here. This is the JavaScript code that you may be familiar with. This is just how we draw balls on excuse me, on context. So basically this just draws it. But here's another interesting point. When you pass a struct, right? I'm passing a ball struct. I'm passing it from C to JavaScript. What do you get? You get a pointer, right? So you can't just say, okay, let me get that and do .x, .y. You can't do that. Rather, you actually need to know how it's laid out in memory. So the way C works, by default, whatever, it puts for every single value, right? This is going to take up, this is 4 bytes, 4 bytes, 4 bytes, right? This is all 4 bytes, I think. So we need to just have the offsets for everything. So the x starts at 0, right? So when you have the struct laid out in memory, at the first spot at the pointer, you're going to have the x value. 4 bytes later, you're going to have the y value. 4 bytes later, you're going to have offset, etc., etc. So it's very, very manual and tedious, where I'm basically reading out using this data through API, which I never knew existed before this, which allows us to read into memory specifically at different spots in that memory and give me access to all the different values that I got. You see? So that's how I'm able to get the x, the y, the raised, and the RGB values, the color values, and that's how I can actually draw them all. Okay. So now we come around and we call draw. Now we call update. Update again goes back into C. Okay. Which one?
What's the Boolean at the
What's the
end?
Boolean?
In
Jobs.
my
In July.
little endian. Yes, there's a little endian. Okay, it's a little endian. For those that know, it's the byte order on your. But it is a little endian, I think. It obviously is. So let's go into the update function. My update again comes from C. What does update do? Update is responsible for all the logic. So on every single frame, not in the ball, sorry, every single frame we're calling update, which basically loops through all the balls. Okay, and I didn't mention this, but there's a balls way up on top. Okay, it's just in static memory. I'm not using malloc because there's no malloc, there's no free, there's no standard library. You could. Right now we're just using static memory, just allocating a chunk, and if we go beyond that, who knows what's going to happen. We're not trying to get any memory saved here, it's not the point of it, right? Which again, since you were writing this overall, there's no standard library, you don't have malloc, you don't have any kind of, you don't have a way to allocate and reallocate and all that kind of, you don't have that stuff. Mscripted gives you all that, we're not doing that. So, we go to update, and we loop through all the balls, we call it move ball, we pass in a pointer, and here the first thing we do is we just update the x and the y, we update the position of the ball based on the current velocity. Then we're doing the basic collision detection. The collision detection is just to get, right, if the bottom of the ball, you got to do the whole cheshbon. If the x is past the bottom, then you want to invert the, I don't want to get into it, it's pretty simple logic, it's not really the point of this. But the point is, in here, all the logic, quote unquote heavy logic, whatever, all written in C. It's the language I'm familiar with, this language, whatever, it's faster. No sales pitch. But this is where the logic is actually done. Once it's all moved around, right? So what we're doing here, we're updating the position of all the balls, and the next time we come around, we're going to draw it. It's going to be drawn in a new position. Again, the logic is done in C, but the parts that we can't do in C, like drawing to the canvas, for that we need JavaScript. Make sense? Then what I also have is in my JavaScript function, not here, in my JavaScript code, I also have on the add event listener, when you click on the actual canvas, what are we doing? Again, I'm calling add balls. What's add balls? Add balls is a function I got from WebAssembly. Okay, right here, add balls. So what I'm doing inside of my, inside here, I need to do a little bit of shticky trickery to map canvas coordinates back to the, not important, but the point is, I get the coordinates of where they clicked, I take those coordinates and I pass them in. So I'm calling a function from C, passing in the x and y of where they clicked. So now back in our C function, if you look at the add balls function, it takes in these x and the y, and then there's all the randomizing shtick of basically creating a new ball. It loops through, I have this macro over here, balls per iteration. For every iteration, we do 100 balls. Point is, it loops through to that number, and just creates a new ball for every single one, randomizes all the values, etc., etc. Okay? So effectively, all the logic is here, but the drawing, the kind of the meat of it, not the meat of it, but the looping and the stuff and the flow of the application and the parts that C can't handle, that WebAssembly can't handle, we're doing in JavaScript. But the logic is all done over. Make sense? Okay. So let's go back to here, and let's go back to our slides. So, here's an interesting thing, but who says WASM can only run in the browser, right? Let's think back. What is WebAssembly? WebAssembly, like we discussed, we understood, it's just a binary format blob. It's a virtual machine. It's a program that we wrote in a few lines of code. Obviously not a very sophisticated one, but it's a program that knows how to execute these instructions and manipulate memory and manipulate a stack, and that's it. Who says a browser is the only one that can do that, right? If WASM is just a binary format for a stack-based VM, who says only the browser? Maybe we could run WASM outside the browser. Maybe? The answer is why yes, we can. So WebAssembly is actually, you can actually run it outside the browser as well. Because what is WebAssembly? If we understand it now, it's just a program, right? It's basically a virtual machine. It's a program that runs this instruction, manipulates memory. It doesn't have to be in the browser, okay? So, demo time. Let's go back over here. Let's go up a level. Okay, so let me first show you the code. This is actually going to be in C#.
before the demo, can you explain why you would want to use it?
I have no idea. I'm trying to be funny, but I'm not really. I'm honestly, like, I'm not. This goes back honestly to why I gave this talk. I'll zoom in a second. Why I gave this talk, it's really, I just found stuff interesting and fun to play with. The why and what the purpose of WebAssembly, I've seen all these shockwave tires online. It's faster because there's no jitting and all that stuff, but then you have people arguing, yeah, but calling back in the job.
It's safe and speed.
I'm not going to get involved. Honestly, leave it for somebody else. There are a lot of cool things that you see online. I know, that's what I'm talking about at the end. I know Figma uses it, and Adobe, they have a Photoshop, entire Photoshop for the browser written in C++. They have a letter. I'll talk about that a little bit at the end, you know, some practical stuff about it a little bit. But honestly, I'm not here. I don't really care. Let's go a little bigger. Okay. So, this is a C# application that I wrote. So there's a framework on Linux called GTK. GTK is for writing desktop applications on Linux. There's bindings for C# called GTK Sharp. I'm familiar with C#, sue me. So I decided to use GTK Sharp to write a little desktop application. This is a Linux desktop application that's going to be, here's the idea. What I'm trying to demonstrate now is this notion that you can actually run WebAssembly outside the browser. So before I do anything, I want to do one thing real quick. I'm going to copy. Go up to my previous demo. This is the demo of the balls. Let me clear my screen for a second. This is a demo of the balls. When I ran it, it generated a main.wasm, or it was my web folder. Sorry, main.wasm. This got generated when I built it, and I want to copy it into my current project, my C# project. Okay, I copied that WASM file. All right, and what I'm about to demonstrate is that this is a desktop application written in C# using GTK. Desktop, nothing to do with the browser, and we're going to load up that same WebAssembly, and all the logic, all that's going to still be there. I'm going to write the parts that I wrote in JavaScript, I'm going to write in C#, but all the logic is still going to be the same exact WASM file, no touches, no changes, right? So let me first demo it to see that it actually works. Please work. Where am I? I messed up one thing. Main.wasm to here. Okay. Well, I already have it here. Okay, fine. Again, okay.
You gotta go up. Go up. Go up.
Two down.
Yeah.
It's great. I wish I could program a bunch of people in front of a bunch of people every day. Make no mistakes. All right, so let's just run it. .NET run.
What does that mean? I'm joking.
There you go. Okay, so it's slower for reasons, whatever, but this is a desktop application. There's no browser now. I'm using i3, so you don't see the typical, like, actually maximizing, this is a stupid window manager I'm using, but it is a desktop application, okay? So you can see up here, this little guy, this is as far as you can get with i3, but yeah, okay? It's definitely a little bit slower, but it works. It's the same program that I'm running now with C#. We're loading up the same WASM thing. So let's kill this, okay? And let's look at the code. So, here we go. So I have a structure here, but let's kind of go to let's start here, okay? So there's something called, we're going to talk about a little bit more in the future, very soon, something called WASM time. WASM time is built by the WebAssembly Alliance or something, Bytecode Alliance or something like that. It's a tool that allows you to write, it's effectively a WebAssembly run, WebAssembly host. And there are bindings to C# and the other languages probably, where you can run WASM time from within your code. So effectively what I'm doing with these kind of, with these 4 lines of code is I'm loading up that same WASM file like I was doing in JavaScript, I'm loading it up now in C#. And then over here, remember I'm defining a function. There's one function that I have to import, right, the way to draw an actual ball. Then I'm doing over here, I'm basically saying define function, platform draw ball, should call this function called draw ball, which I have down over here, okay? Which I have to do again some trickery to get, because remember we get past just the pointer. So in JavaScript we read out bit by bit. Here we're using some memory marshal.read. High level, same idea. I'm getting a pointer. I need to now take that pointer and convert it to my ball thing, and then I'm using some GTK Sharp shenanigans to actually draw the screen to the ball, to draw the ball to the screen. Okay, but it's the same program, same flow. I don't have any act over here. There's no logic about moving and updating, none of that stuff. All that's still being done in WASM. I'm just providing whatever I was doing previously in C#. So let's look at the previously in JavaScript over here. We have this little loop that everything constantly basically just paints, restores, and just basically update and draw. Same exact loop. Everything else is just this GTK stuff. But update and draw, same basic idea. It's going to do the same loop, and it's going to draw. But instead of draw now calling to a JavaScript canvas API, it's now going to call to our C# GTK, and it's going to do it. So WASM is useful not just in the browser, it's actually useful outside the browser. Going back to my very hyperbolic name, that's why I said terribly named, because it's not assembly, and it's not just the web. So WebAssembly is entirely free. Okay, very cute. That's really the reality. So, cool. So let's go back into our slides. Right. So, being that that's the case, that we can now run WebAssembly outside the browser, right? And this is actually something where the industry is really kind of running with, in a sense. And again, I'm not really predicting any futures, or I don't really know, but there's definitely people that believe that WebAssembly is going to be more popular in a sense outside the browser, or at least, whatever, if it is popular at all. But the point is that imagine a scenario where, in fact, there was this one tweet from the guy that created Docker that said that if WebAssembly existed at the time when he created Docker, he wouldn't have needed Docker, a whole back and forth. But conceptually, what we can think about, being that we could run WebAssembly outside the browser, imagine a scenario where we can just upload, instead of, when we have any kind of cloud hosted solution, instead of uploading our application, we just uploaded a WebAssembly module. We just upload WebAssembly, and then we can write an entire application WebAssembly. Now, obviously, we're going to need to be able to make network requests and be able to do a bunch of things dealing with the actual machine itself. So we're hopeful that the platform that we run our WebAssembly on is going to provide, they're going to import those functions to us. That's the idea. It could very well happen. Again, we're going to take our WebAssembly, upload it somewhere, and in our C code, quote unquote, we're going to import, we're going to know which functions are going to be imported to us. Yeah, if we're going to do it, let's say, on Microsoft Azure, Azure will tell you when we run this, here are the functions in order to write to a file system, here's the function you should import. You want to do a network request, here's how you do this. So we can take our WebAssembly, upload it to there, and then they can run it. And we can write it in whatever language, because you can compile pretty much nowadays any language to WebAssembly. The problem with that is then obviously every single different host is going to have a completely different set of standards, which is where WASI comes in. So WASI essentially is that, it's basically, let me read this. So now that you can run WASM applications out of the browser, imagine a world that where you can upload a WASM module to some remote host that can run our application, let's say an Azure function or AWS Lambda. We can take our WebAssembly and just run it up there. It doesn't matter what language we started with, we end up with WASM, push it up onto an Azure function, and they're going to run it. But how do we know which functions are going to import it to us? Right? For that reason, there's this concept of WASI. WASI is basically just the standard stands for WebAssembly interface, systems interface or something like that, which effectively is just, it's an interface. It's just a set of guidelines or a spec, I guess is the best way to think about it. It's just a bunch of functions that if you're WASI compliant, here are all the functions that you're going to be importing into the WASI. So if you're a WebAssembly runner, if you're a tool that's running WebAssembly, and you're WASI compliant, these are all the functions that you're going to provide to the WebAssembly module when you're running the WebAssembly. That's what WASI effectively is, okay? So, there's another tool like I showed before, something called WASM-Time. WASM-Time is a fast and secure blah, blah, blah. Using WASM-Time, we are able to, like I showed before in my C# code, we can run WebAssembly outside of the browser. And WASM-Time is in fact WASM compliant. Meaning, when you run something with WASM-Time, you in your WebAssembly code can rest assured you're going to have these WASI functions provided to you by WASM-Time. And you have to look at the actual spec of what WASI is to see which functions, but the point is when you're running your WebAssembly outside the browser, you're running it through WASM-Time or any other WASI compliant runner, clearly you know which functions are going to be available to you, so you can easily interact with the system. You need to write to a file? Okay, how do I write to a file? Why? You have a whole interface. You don't have to provide the function yourself, obviously. WASM-Time is going to provide it, and you just call it into it because you know it's going to be there. Okay? So let's start a little demo of that. Okay, so let's bring that up in VS Code. Okay, so very similar to before, all my C stuff, except so it's a little bit more complicated. But let's just start with this. So if you look at the actual spec in WASI, one of the functions that it provides is something called fdwrite. Fdwrite stands for file descriptor write. File descriptor is what we write in file descriptor Linux, whatever. So this is how we write to files in WASI, right? So we have this fdwrite function. So what we're saying over here is this function, this my C function, underscore WASI underscore fdwrite, this is going to effectively map to the imported function that's going to be provided to me. Remember, it's import. When this code is run, it's going to be provided to me by the runner. This function will be provided to me as fdwrite. So now in my C code, I can actually call it. It's a little bit of a complicated function. It's not so simple. You have first the file descriptor, the number of the actual file descriptor. Then you have this weird struct called the WASI-CL blah, 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 which is a simple struct that has two things in it. It's got the actual text, and it's got the length of the text. And then the other thing we can kind of ignore, okay? But what I'm trying to demonstrate here is I'm calling this function, I'm passing in 1 as a file descriptor. So in Linux, the way it works is that everything on Linux is a file, as we know. So in order to write the standard out, if you write the file descriptor 1, that maps the standard out. So when I call this function, which effectively is built for writing the files, and I pass in file descriptor 1, this is in the C program, which technically is in WASM, which has no access to the outside world, but I'm going to run this through WASM-Time, which provides WASI functionality. I'm calling this WASI function, passing in file descriptor 1, it's going to write hello world to my console. Let's see if that's true. And there it is. And there we go, hello world. This is a program that was written in C, compiled to WebAssembly. If you don't believe me, you go to the makefile. It's compiled to WebAssembly. Okay. But when I run it, I'm using WASM-Time, saying invoke the main.wasm and call the hello world function, which is a function that I export here from C.
How long here you need extern?
It's a good question. I don't really know. You probably don't. I don't know if I probably don't. I don't remember trying to cover this from somewhere, so I probably had extern. Honestly, that's probably what happened. Good catch up. Oh, sorry. All right, let's go a little bit more because I see people are starting to lose patience. So let's go quickly. So now let's get into a little bit more, I guess, right. So up until now, this is how you don't write WebAssembly, right? This is how you do not write WebAssembly. This is just to give you an understanding of what WebAssembly is. So let's go a little bit deeper, maybe how we could potentially use WebAssembly. So again, this is where I'm going to stick to the .NET world because that's what I'm familiar with. But from what I've seen online, many different languages. Rust is like seems to be the most popular. Like when people write a lot of WebAssembly, it seems like Rust is kind of the forefront of this. But many different languages have bindings to WebAssembly. You can compile the WebAssembly. So people out there doing different languages, you can correct me if I'm wrong. But I'm pretty sure I've seen for a lot, even Ruby and Python, and dynamic languages, and even whatever. So there are ways to go. So I'm going to stick to the .NET world, and I do think .NET in a way is blazing some trails here, no pun intended, but they are kind of a little bit forward-thinking with this stuff, which is kind of interesting. So let's first look at this guy. So let me pull this up over here. Okay, so I have this little program here. There's something in .NET that they added, something called WASM experiment. WASI experiment. Let me just use this thing. Okay, so for those who aren't familiar, basically I'm using this package called WASI SDK, which is a package provided by Microsoft, which is still a preview version. It's totally still an experimental thing. It's not really whatever. The point is, I can write a program, okay, that this program, all it's going to do is going to say, run them information.os architecture. It's going to print out the architecture of the OS, which in my case, Linux, I'm x64, it's going to be x64, okay? But since I'm using the WASM SDK, the WASI SDK, when I compile this, it's also going to get compiled to WebAssembly. Let me show you. We go back to the command line. I'm going to do here, .NET build. Okay, let's go into our bin, debug net. It's in here. There we go. So now I compiled these two files I got. Actually, you can ignore this stuff here. There's a WASI console. So if we look at that, we look at file WASI console. Let me screen again. WASI console. That should be an ELF executable. This is an actual native executable that wraps whatever dynamically linked. Point is, this is an actual executable. And if I were to run this again was compiled by my .NET run. If I run this, I get running on x64. However, now what I'm going to do is I'm going to do WASM time. WASM time. Remember that guy? WASM time. And I'm going to pass in /WASI console dot not the L dot where is dot WASM. Okay, and on WASM. So same program again. I wrote my regular comfortable C#, just some different compiler flags, and all of a sudden now I have my program running on WASM, and I didn't do anything about WASI, right? I didn't do any FD writes or anything. I just did my standard console write line. Again, for those that aren't familiar with C#, console write line is the standard way to write to the standard out in C#, and I just ran that line of code, and boom, it just wrote it out without me having to do anything fancy. And that's kind of the abstractions we're going to start really building as developers. That's where we're going to be living in this stuff. Just reference a few packages, and write your program as normal, and all the underlying bindings to WASI and all that's going to happen by itself. Okay, let's show another quick demo. Let's move to the web a little bit. Where am I? Okay, let's go into, where am I? 8? 8. No, 9. Okay, so this one is, let's bring this up. This is another project type for Microsoft, which is also very much experimental, which is a way that we can use WASM in the browser. So if you look at let's go to main.js. My main.js, I just have this, I import this .NET function, which is provided by Microsoft. This is not a function I wrote. This takes care of all kind of the magic binding. I'm purposely not trying to understand what it is. I want to kind of drive the point home. We're now abstracted away. We're just using what they're providing, these APIs, and things just work. So for example, over here, I have in this, I have this little function over here, exports.myclass.download.msg. Okay, what is that? Okay, that's a function. If you look at my program.cs, that's a function that's written in C#. Okay, so in JavaScript, I can access a function just like I was doing before. I was accessing C. Now, without me having to think about anything related to WASM or WASI, it's just you take this file, this program, compile it to WebAssembly, and now we can just use a .NET API to just basically say, hey, get me that .NET, just whatever this is, and just get me that thing and run it, and boom, I can now call for my JavaScript straight into my C# code that was compiled to WebAssembly. So this is an actual potential real use case, somewhat. So at Madison, we actually have this need for generating MSG files. So for those that are familiar, MSG files is the native format for Microsoft Outlook on Windows for their emails. Okay, so if you take an email in Microsoft Outlook and you save it to a file, it's an MSG. It's a proprietary format, I think, for Microsoft Outlook. So the users, we had this on this one application, we had this need where people we have to generate emails. They wanted to be able to email to see it in Outlook. They wanted to be sent from Outlook. They wanted to stay in Outlook. So we came with the idea of just we can generate programmatically. We can generate MSG files. So I looking into it, I was like, are there any JavaScript libraries to do this? There's one paid version. Recently, I saw there is a new open source version, but at the time, there was really not much there. There's really not much in the way of generating MSG files from JavaScript. Okay, now obviously everyone's going on tonight and Slack me, including me wrong, I get it, but that was the reality at the time, right? However, in C#, there is a library called MSGKit, open source library, that does beautifully. It handles it very, very nicely. So what we resorted to doing is we made an API call to the back end. That's where C# is generated and send it back to the front end. Very nice. Can we do it on the front end? And the answer now is yes. Being that we can write C# on the front end, and this MSGKit library, all it's really doing is just manipulating bits, right? It's a file, we're just creating all this thing. And right, so with this, I was able to, in the C# project, which is going to be compiled to WebAssembly, run on the browser, not on the server, this, I was able to use this library and use their very simple API and just return an array. So this download MSG file takes in a bunch of, again, takes in strings, no pointers. I'm now in my familiar territory, right? Taking a bunch of parameters, send back a byte array of my actual MSG that was generated. And now if I go to my JavaScript, very simply, I can then just call my function, download MSG, which is going to call my WebAssembly file, call my C#, pass it in, get my byte array, and then just turn it into a blob array and just append it to and turn it into a download link. Let's run this. Wait, I can't run this from here. Never mind. Okay, so it's already built. This is a funny thing. Never mind. I'm just not going to explain. We're just going to make believe that didn't happen. So this is a little thing that I built. Again, this is the HTML page. So if you look at the actual code over here, this HTML page that I have over here is what you're looking at. This HTML page has got the JavaScript. But just to show you real quick, I come in here, I'll say to Lakewood at devs.com, meetup at should.in.net, and hello, we're set. Okay, click download MSG, and this now calls it, and downloads this excluded MSG. And just to preview this real MSG file, I have this little tool here. Let's open this up here. We've got, I think, say Java some Java application to view MSGs on Linux. MSG. Let's make downloads. From MSG. Okay, so I don't know if we can see this, but yeah, this is my MSG viewer, and you can see it generated an actual MSG file. It worked. Okay, so it totally worked if you want to. Okay, let's kill that. Let's kill that.
How do you know what you can use from C#?
How do you know?
What you can use.
So for the most part, you can use a lot. So you have to, again, you have to remember that you're still running in the browser, right? You're still running in the browser, right? It's a good question. So writing the files, I don't know. I don't know if they have a way, because you could think there are some file system APIs in the browser as well, so it might map to that. I'm not exactly sure where it is, okay? In Blazor, it's a little bit more well-defined, and this still seems to be a little bit more the Wild West of what I'm doing, okay? Read the docs, effectively. You gotta kind of know what they, but there actually is, surprisingly, WASI is meant for the server side. I was talking about being able to access on the server side. There is a WASI implementation for the browser as well. And this guy, Steve Sanderson, actually, the guy at Microsoft that's always, the head of he's the one that built Blazor, he built this mind-blowing demo where he got an ASP.NET Core, which is the framework for .NET server-side framework for building web applications. He got that running completely in the browser. Because he compiled the WebAssembly, ran in the browser. And by the way, SQLite, right? There's actually a version of SQLite that compiles the web, and you can run an entire SQLite database in the browser. So stuff is real. So again, I'm going to talk about practical in just a second, but there's a lot of cool things you could technically do. Okay?
You play Doom?
And you definitely can play Doom with the browser using website. You can play Doom on anything. That's not, you can play a lot more than Doom, but yes. All right, so let's go back over here. Okay, one more demo, and I promise you I'm done. Okay? So this is Blazor. I don't know if you guys have heard of that.
No.
So
What is it?
Get in there. Can't tell if it was a joke or not, I'm not sure. But anyway, so
It wasn't.
it wasn't. Fine, so I'll explain it. Blazor is really kind of the one area I would think that I would say where this is kind of like we're furthest abstracted away from WASM, and it's actually useful. It's actually could be potentially kind of useful. So the idea that Microsoft had is what if we could write our entire full stack, backend and front end in C#. And we're not talking about C# compiled to JavaScript, we're talking about taking our C# application and compiling it to, guess what? WebAssembly. And that's effectively what Blazor is. Blazor is an entire, there's two flavors of this. This is a Blazor server. It doesn't touch WebAssembly, but Blazor WebAssembly is an entire front-end framework with everything that you need, right? Including routing, including data binding, including everything that compiles down to WebAssembly that works in the browser. So and this is a bare bones app. I usually do .NET New. It just spun up a new. I didn't write a single line of code. This is just the template that they give you out of the box. We can explore it briefly just to see how this works, okay? So first of all, the server application, which basically has this one endpoint over here that's controllers. Again, for those in the MVC paradigm, there's a single controller here action where you basically make a request to slash weather forecast. You do a get request, you get back a bunch of weather generated random data, just in weather objects. Okay. Then we have in our front end, we have over here, let me run this actually so you can see it first. Okay, let's.
How's it access that?
Do you need JavaScript in the end?
So all good questions. Give me just a second. Leave this over. So, again, I didn't write a line of code here, but we got this hello world, it's got routing. If you look at there, it's got this routing, we got the little typical click me, and then we got the fetch data, which actually goes ahead and gets a fetch request and gets our fake little weather data. Okay? So all this is kind of just out of the box. This is all done. There's not a single line of JavaScript that I have to write. This is all done in C#. Okay? So, let's look at how we use this code, and then we'll kind of come back to it. So Microsoft has a templating language that they've used for a long time in the backend called Razor. Not important, but effectively, if you just look at it briefly, we have this as the counter page that you saw counter. So this is how you do routing, and then this is how we do have this variable here. This is our C# code. We have this little current count, so it uses this data binding concept. So every time this increment count, every time this gets incremented, basically this little value gets incremented. So we got this binding here to increment count. Again, for those familiar with any kind of front-end thing, this looks somewhat familiar, but the point is that code is C#, it's not JavaScript, okay? Furthermore, if we go to our, this is where I think it's really cool, we go to our fetch data page, this is actually kind of nice. If you look over here, where we have this is sort of like our component and mount, quote unquote, we're using this HTTP get based on the scene, which is this, basically there's a class in C# called HTTP client. This is how we make web requests in C#. And notice I'm on the browser, and I'm making the web request using my familiar C# thing. Blazor handles all the machinery under the covers, how they tie that back from WebAssembly back to our JavaScript code. They handle all that for us. I don't need to think about it. And C# is just like, okay, in order to make a web request, use the HTTP client to make a web request. And this is the great part about it also, is this weather forecast class is a class that's in a shared project that are shared by both the client and the server. So this is what you get when you build a full stack application. Again, this is not the only way, and I know you can do it in TypeScript, I get it, but what you get here doing this way is you have a shared code effectively that you can share both between the client and the server using, because the front end is completely in WebAssembly, completely in C#. So you had a question, what did you say?
How's access that?
So they have a whole DOM diffing algorithm, they do all that kind of stuff, but I don't need to access the DOM directly, it's just like you're abstracted, just like you are in React.
Hey, but somewhere it has to reference.
Oh, it does, of course, it has to, yeah, because again, WebAssembly by itself is like this, its hands are tied, it can't do anything. So in order to access the DOM, it has to go through some layer of JavaScript, and access it does whatever it needs to do, yes. And I think that about wraps it up. What's saying?
How does debugging work on the front end?
For Blazor? Honestly, I don't know how they keep improving the story. It's not great. It's not great, but they have some kind of bindings where you could actually debug your C# code in the browser using Chrome DevTools. It doesn't work that great, but technically you could. Okay. So I just want to end off with. I just want to end off with just, if you go over here, Blazor. So there's a website here. It has some cool, impressive demos. Now, hopefully your ears won't bleed, I don't know, but let's just do this real quick. Okay, now I'm not good with keyboard mouse, and I'm using a little trackpad, so don't make fun. Actually, I should have done Revolution. Whatever. But this is a full-blown game written in WebAssembly. Web is using, why is my thing not work? Let's do this. Okay, let's try to quit. Let's try one more time. Let's do the high resolution version if we can. High resolution, there we go. Okay, there we go. Okay, so this game was built using WASM and using WebGL. WebGL is another API in the browser to actually access your GPU. But again, this is what's possible with WebAssembly. You can build full 3D experiences, full 3D games in your browser using WebAssembly. And in fact, what I found out recently is that Unity, for those that know, is a very popular game engine. And again, also you have OWASM targets. You can build your games using Unity, and you can build it for the browser, which is pretty cool. Okay. Also, Figma, and a few other examples I'll just talk about real quick. Figma, I know, is one of them. I know Photoshop also, but there's basically a lot of companies that have either had a large, like Adobe for Photoshop, they had an existing code base in C and C++. They were able to compile it to WebAssembly, and now we have a full Photoshop in the browser. Not full, but it's a very functional chunk of Photoshop working in the browser. Figma. I don't know if you guys have ever used Figma, pretty responsive application. They also made a decision, hey, it'll be faster and better to run it in C++. I'm going to stay away from all the hyperbolic faster or not. Again, do your own research. I don't really know. But the fact is that there are companies using it and doing it. Bottom line, at the end of the day, the reality is most of us here are probably never going to use WebAssembly. That's my opinion. I don't think it's ever going to do anything. I just thought it was cool, so I wanted to talk about it. I don't really know where it's going. It's been around for a while. It hasn't really gained much traction. So honestly, I have no idea. It's just interesting to know about, and I thought it was interesting to talk about. So that pretty much wraps it up. If anybody has any questions, let me know. But that's pretty much it.